nowadays, applications based on physical-human-robot interaction, PHRI, have been widely seen. And PHRI means humans are in direct interaction with the robotic system to accomplish tasks. The application scenarios including medical robotics, for example, the robotic surgery and the exoskeleton rehabilitation. And during the PHRI, there are two things that are critical and have to be guaranteed and optimized for between the humans and the robots. The first is the safety of the interaction, and the second is the transparency and the fidelity in the information transfer. For example, we want the force applied to the human to be as close as the force generated by the robots. In order to guarantee those perspectives, there are some solutions and methods that has been proposed in the literature. So for example, one popular structure is the time domain passivity approach, TDPA, which has two components. The first is the passivity observer, PO, and the second is the passivity controller, PC. So the passivity observer will keep observing the system energy level, and based on that, the passivity controller will adaptively modulate the velocity and force to guarantee the system's passivity and thus stability. However, even though the system can stay stable after implementing the stabilizer, the cause is that the delivered force and velocity are modified, and the system's transparency is degraded. So in order to improve the transparency of the system, some researchers have incorporated the human spark mechanic into the stabilizer design, which means that when we are designing the stabilizer architecture, the energy absorption capability of the human, which is relating to the concept excess of passivity, is taken into account. So they use this amount of the energy margin to absorb the energy that is supposed to be dammed out by the stabilizer, resulting in less activation of the stabilizer, and that has a better transparency. And more detail can be checked in our recent paper published in IEEE Transactions on robotics. And currently, we quantify the energy absorption capabilities through an offline identification process. The outcome is a geometric MyoPassivity map, GMP map, which can visually show the energy absorption capability under different conditions, such as directions, interaction frequency, and also the muscle co-contraction condition. And we have identified the 2D GMP map in the force velocity domain and the 3D GMP map in the force position domain when we including the frequencies context of interaction. And more information can be checked in our recent paper in IEEE 2023 and IROS 2023. However, so far, the identification process needs to conduct every times before the experiment, which can be very time-consuming and cause the user to become fatigued. And also, the PHRI system needs to be reliable and to be used repeatedly. So in this paper, we investigate the Interday's reliability of passivity map of healthy subjects to see whether the passivity map identified in one day has a high similarity that the passivity map identified in the next day. If so, then the passivity map can be set to be a unique, reliable, and repeatable biomechanical signature, and therefore does not need to undergo another identification process in the Interday's experiment. So, as a basic overview of the framework, we discussed the definition of passivity and the output strictly passive condition from strong passivity theorem. The passivity-based definition of the total energy of an M-port system depends on the summation of the energy of each input-output port. The energy is computed as the integral of the input times the output. For the system to be passive, the energy in the system must be positive, meaning that the system dissipates energy instead of generating energy. The output strictly passive condition defines an additional margin that encodes the extent to which a system is passive. The margin is encoded as the coefficient psi, and this can be considered as the excess of passivity when positive. So we have created an experiment set up to measure the excess of passivity of the participant in our study. The participant is sit so that their elbows make a 90-degree of angle when holding the handle of the robot at the indicate center location of the GUI. And the electromyographic EMG sensor are placed on the arm to measure the muscle contraction level of the forearm. These are processed into two bar graphics showing the percentage of muscle contraction compared to the maximum muscle contraction of the forearm. And this is provided as a visual feedback to the participant. At the same time, the robot perturbates the hand at a set frequency with no velocity profile. The reactive force is measured and the excess of passivity is calculated. For our experiment, we measured the excess of passivity of the upper limb under two different levels of muscle contraction, the relaxed condition and the stiff condition. The relaxed condition is when the users hold the robot handle at or below than 5% of their maximum voluntary contraction. And the stiff condition is that we ask the user to maintain 40% of their maximum voluntary contraction. We also apply the perturbation for 8 different geometric directions on a 2 consecutive days with 24 hours gap. And each perturbation lasts for 10 seconds, and there are 5 subject participants in the study. So these are the resulting interday passivity map for all subjects on both days. The upper row is the result of the day 1 condition, and the lower row is the result of the day 2 condition. And the blue dot is the excess of passivity of the stiff condition, and the red dot is the excess of passivity of the relaxed condition. And each column represents the interday map from different subjects. And as can be seen, the excess of passivity value in different directions are varied for subject and between subjects. Also, under the stiff condition, the identified excess of passivity value are significantly higher than the excess of passivity value identified during the relaxed condition. And this observation can be seen in each direction of perturbation. More importantly, when we visually compare the excess of passivity value from day 1 and day 2 for each subject, we can see the shape and the magnitude of the excess of passivity for the relaxed and stiff condition are similar and well preserved. This observation is seen for all subjects. And beside the observation, we also conduct a statistical test to compare between different groups of data. The left figure is the violin plot comparing the excess of passivity between days and muscle co-contraction condition. For given days and muscle co-contraction condition, the excess of passivity of all 5 subjects in all 8 directions was combined together in a single distribution. We consider a p-value lower than 0.05 as statistically significant. And for both days, the excess of passivity was significantly higher for the stiff than relaxed condition. And for both relaxed and stiff condition, there are no statistically significant difference between day 1 and day 2's data was observed. So on the right figure, we also conduct the statistical test between the day 1 and day 2 excess of passivity value in each direction. There are no significant difference was observed between the excess of passivity distribution of day 1 and day 2 for all directions for relaxed and stiff condition. And after observing there are no significant difference between the excess of passivity value across days, a formal reliability test was conducted. We calculate the intra-class correlation coefficient ICCC1 from the case 2A model of the following paper. The ICCC1 indicated the level of consistency between the 2 sections and can be interpreted here as the reliability of the measurement obtained from a single section. And the intra-class correlation coefficient in each direction for relaxed and stiff condition is calculated. The Fields scale is used to interpret the ICC's value. Intra-class correlation coefficient value, if greater than 0.75, means that the test data has excellent reliability. As can be seen, for all geometric direction and for both muscle contraction level, the value of the ICC is greater than 0.75, which means that the interday excess of passivity identification show excellent reliability across all conditions. And in conclusion, we have shown that the passivity map created from one-shot observation represents a unique, repeatable, and reliable user-specific biomechanical signature of the energetic behavior of the upper limb during the physical human-robot interaction. Therefore, for the first time, the results suggest that the passivity map can be used reliably over multiple days of the physical human-robot interaction without the needs for re-identification and recalibration. And thanks for attending this presentation. This work was supported by the US National Science Foundation. If you have any questions, I'm happy to answer. Thank you.